G'day, we're back in what could be comically called the studio, and today we're looking at a kiln controller. I'm going to cheat the kiln's interlock to demonstrate what happens inside of the white box when power is switched on continuously by a solid-state relay. It glows, and it glows hot. That is mains voltage through what was formerly a fan heater. That has now cut out with an automated Python script, which is running on the device, the Raspberry Pi, and accessing the solid-state relay via pins that have been broken out. Wiring has been performed with Wago connectors and other such devices. This is where I say, disclaimer, all electrical work must comply with local regulations, and also have a safety switch in. This safety switch is in line with the control voltage signal so that it can be interrupted by the user, for example, when a kiln door is opened. I will now switch to displaying the kiln in normal operation, which is not exciting at all, because you switch to just watching a trace on a screen. While the box is open, I will point out the thermocouple, which is a toy thermocouple. If you read the documentation of this Python project, you will find a funny note which says, "Invest in a better thermocouple." I would also not recommend building a kiln like this out of fiberboard. This is a demonstration kiln. You don't have to rip into me in the comments by telling me that this kiln won't do very well. I know that. And I have only succeeded in getting it up to 700 degrees Celsius. Because at the end of the day, you can only push so much current through these elements. You need to switch to proper millimeter gauge cancel wire if you'd like to do pottery work. And there are exciting new elements, silicon carbide elements, which might make a good build in the future. Alright, that should be enough footage for the introduction of my hotbox. Today we're demonstrating a kiln controller, which has been built from an open source project by jbruce12000, and I will provide the link to the GitHub repository, which I believe he forked from the Pico Reflow project. How does it work? It uses a Linux Wi-Fi enabled board to read from a thermocouple reader. I've used the Adafruit Universal Thermocouple reader. It also switches some pins to get status LEDs that I'll describe in detail later. And it has headers that are broken out to peripherals, such as a solid-state relay, which does high-power mains voltage switching for inside the box, which is the kiln controller, which is the kiln that I demonstrated at the start of the video. Now, I've put the lid on the box, and if I lift it up and I pop it back down, you might hear the safety switch clicking. So that lid keeps the heat in and the switch depressed, which then allows power to flow, because the control voltage on the SSR, which is low voltage, passes out through the switch and means that you can interrupt the power by lifting the lid. You will note a fan inside the solid-state relay enclosure, which is, in theory, able to blow heat out of the box if you fit it with a mesh for that purpose. All right. Now, why does this project exist? It exists to provide functionality, open source functionality, to allow you to control and tune your kiln using Python programs that are running on the Linux computer. And here's an example program, very simple. It goes from 50 to, well, you can edit whatever you like, adjust by click and drag or by numerical entry. 200. Let's try for that in 1 minute. And save that profile. And at this junction, I will talk about the status LEDs and what they mean. The first status LED, which is broken out, tells you that the web server is running. The second status LED tells you that the program is running. And the last LED tells you that the SSR is switched on. So if you have a box that doesn't have a clear lid, you can break that LED out and put it on the enclosure as you like. Now we can see that our trace is trying to follow the profile and it has overshot. So I've configured, or I have left the configuration in this project which says if there is an overshoot, then wait until the temperature comes back inside the desired range, desired control range, before continuing the program. Similarly, I have left in the configuration option to jump ahead a little bit, to jump ahead to where the profile is if the kiln is hotter at the start than the starting profile calls for. Cool. Now, that web server also lives on the Linux computer, even though it doesn't look like it. And I am currently connected to that Linux computer as if it were a router or an access point, to use the correct terminology, at this IP address, and I'm connected to it as a Wi-Fi point on this laptop, which takes some setting up to do in Linux land. Now, I keep mentioning Linux land, and you can get to that Linux land on that computer from another computer using SSH, which I will demonstrate. I've exited using the command terminal, and I can now SSH into the furnace at the IP address of its access point, if you connect to it. You can also SSH to it other ways, but this is the way I'm doing it today. Now, you could remember its password correctly and enter into the Linux terminal on board that. Enter into a Linux terminal on board that computer. And I can clear, and I can demonstrate a few points of interest, such as the fact that this program that sets up the web server runs automatically on start, and I can stop that function to demonstrate some other parts of the program. So I need to do that, or else there will be conflicts with when the board is cooling for temperature readings or sending switching signals. So how do we do that? We go sudo system ctl status to check it first, kiln controller. We can see that it's active, and we want to deactivate that. So we go sudo systemctl stop kiln controller.service, check the status again, and we see it's inactive or dead. Cool. So, clear? Now we can use some Linux commands because we're in Linux land, like list, and we can cd into where our kiln controller is. So we go cd kiln controller, and now we'll see all of the project files that are in the Git. The GitHub, which was created by, or forked by, Bruce 12000, and which I've forked further for my programming changes to indicate the status LEDs and switch pins around. Now, the configuration, which I mentioned, lives there in config.py, but today I'm interested in demonstrating, for example, the thermocouple. So I can not directly run these files. Well, I could, but I need to use a specific environment, a virtual environment, which is a specific smaller version of Python. Smaller version, it's a specific or dedicated version of Python with dedicated packages for this project, dedicated dependencies for this package, for this project. Now, how do I activate that venv? Well, I have to go source, venv, bin, activate, and now I have a new little line at the start, which is the virtual environment. And if I said Python, then suddenly I'm in Python land, and I have a little Python line where I could say a equals 1, a, print out 1. Great. But I'm not interested in being there, so I'm going to exit that, and I'm going to go Python to tell the command line that I want to run a Python program. Test thermocouple.py, and here we are. Currently, I'm getting a readout 84 degrees Celsius on that thermocouple. Wonderful. So I can stop that program and I can demonstrate the kiln tuner, which won't give me correct values, but demonstrates the way that this has been set up and the way that you need to use Linux at present to tune this controller for whatever kiln you have. How do we do that? We go Python. Well, let's go read the repository. List. We want kilntuner.py. So we go Python kiln tuner.py, and what it's going to do is run the box up to 200 degrees Celsius and then cool it. So we'll watch that and we'll see it glow. See the box glow. There it goes. Oh boy. And now it will cut out and cool. Once the box is cooled sufficiently, there is a Python program which will run a PID curve fitting on this data, and that will give us a PID value that will give us PID values that are in theory good for this kiln. They won't be accurate because I'm starting hot. I'm starting at, well, I started at about 80 degrees Celsius, I believe, and it recommends you to start cold at 30. The documentation, that is. So we've almost cooled down below 205 degrees Celsius. And now the program has exited after giving us PID values that we can then enter into the configuration file. So that's how you can turn on and off the web service, how you can test the thermocouple, for example, run Python in Linux land, and run a tuning program in Linux land. So in theory, what you would do now, you would write these down. You would then go into the editor, a text editor, a Linux text editor, by going sudo nano config.py. And now we're in, this is Python code displayed to the Linux terminal. And we would go down, we can set all kinds of fun things in here. For example, configure your board pins, configure which thermocouple reader you're using, which thermocouple you're using, if you're seeking to start or not, how long you wait before you make decisions, and what we're interested in now, the PID values that you would then enter to control your kiln. Now, I could understand this better, I admit. Well, let us restore the function of the system, because right now, if I try to reconnect to this website, it would say unable to connect because the web server is not running. To restart that, we would go sudo systemctl start kilncontroller.service, and we would find that we have the kiln controller up here again. So I can say start the run. We'll see that it skips ahead again to there. It's going to try heat up. To catch up, it's going to completely overshoot. But now it's reached that peak, it'll overshoot and it will cool, and it might, to maintain the temperature decline, the temperature ramped there, it might occasionally pulse the solid state relay. So I will let that run and I'll report back and we'll see how well it follows. Welcome back. Here's the white trace for the cooldown profile, and it's doing okay. I'll make an extra note that it appears the ramp that I've set is too fast, and for that reason the program is pausing so that it can basically report back the correct ramp decline. That may not be desirable, and you can configure so that you always have an accurate picture across time what your kiln is doing, what it is actually doing, versus when you want it to do that. That is the wonderful part of a configurable open source controller. Now I'm demonstrating how I would tune this controller, or values that I'd like to change based on the performance I've observed. I've started by stopping the service. Next, I will go into the configuration file. I was already in here earlier, and what I did was I changed the sensor wait time to ½ a second, which is down from 2 seconds, so it should be 4 times more responsive in theory. And that means if I'm getting an overshoot, it should stop sooner. Additionally, I would like to turn off kiln must catch up. By saying false at that location. Now I've saved that and I can exit, I can restart, my kiln service. I can return to my website, and I can try running the same program again. If I say stop, I'll now say start, and I will monitor how well this ramp rate follows, which it should be able to achieve, I believe. We'll just watch. You can see that the relay is pulsing more frequently, and it should decide, oh, looks like I'm going to overshoot, cut out. And so it has. Thought it was going to fall a bit, so it's pulsing, pulsing, pulsing again to try and maintain that profile. And it should cut out so that there's a bit of overshoot, which there is. And now we should see in real time, over the next 8 minutes, how that temperature profile declines and how the solid-state relay fires to maintain the downwards ramp. On observing that, I think I'm reasonably happy with the current tuning parameters. But somebody that fires ceramics for a living might disagree, and they may want a different behavior from the system. Here we are, we're declining. And I'll probably leave this running and speed it up in post. Now I believe we're seeing a classic log decay curve here for temperature. And that profile is probably what is fitted for the PID. What I can do is I can cheat the system a little bit by opening the lid, which I'll do like this. It is now open at the back. And this is the kind of thing where you might have, and this is broken out in the jumpers here, a second cooling system where you might activate a relay or start blowing a fan. But I believe you should be able to see now that the ramp is declining faster, and that should lead us to some actual pulsing behavior in a little bit. Well, I think I'm being optimistic with the cooling rate. So what I'm going to do is pause, let it run out, and report back. All right, I believe that our paths here, our real temperature profile and our desired profile, are not going to cross. So I will pause this run. I will end this run. And I will run through my final pitch, which is to say, what is this project? It's an open source board. It's an open source Python program. Not mine. It's been forked, which allows you to control high power and tune that switching with feedback from a temperature reading that you're taking from whatever box you have, from whatever kiln you have, such that you can, in an understandable way, control resistive elements for your desired application. And that could be glass casting, it could be metal casting, it could be heat treating metal, annealing, or it could be pottery. So the board is available online. I believe you can co-produce it with PCBway, and some of those funds may go to me. Thank you very much to Jay Bruce. Thank you, Jay Bruce, for forking this repository and breaking it out into this application. And thank you for watching. This is the end of the kiln controller and hotbox exploration episode.